Welcome back to Statistical Methods. Um, in this video, I will be covering the second half of Chapter 1, covering frequency tables, histograms, and graphicacy. Now, last class we learned about the distinction between variables, values, and scores, and the different types of variables that exist, such as equal interval variables and categorical variables. But today we will start thinking about various ways to visualize a collection of scores. Now, frequency tables are a quick way to visualize a set of scores, and they answer the following questions. Number one, what is the most common value in the data set? And two, are the scores very spread out or lumped together within a limited range of values? So the organization of a frequency table is as follows. In column 1, you have all of your possible values for the variable. In column 2, you have the number of cases in your data set that have that value, or in other words, the frequency of that value. And in column 3, you have the percentage that each value's frequency is of the total number of scores. So to calculate this percentage, you divide the frequency by the total number of scores. And column 4 is optional, but it can show the cumulative percentage or the percentile, giving the percentage of scores up to and including that particular value. Now here's an example of a frequency table looking at the number of students rating each value on this stress scale, which ranges from 0 to 10. So in that first column, you can see the entire range of possible values on the stress scale. And in column 2, you can see the frequency of scores for each particular value. So one person had 0 stress, whereas 3 people had level 10 stress. And the most people had a value of 7 on this stress scale. At 23.3%, column 3 is displaying the percentage of scores for each value. So to make a frequency table, in your first column, you must make a list of all of the possible values. And in the second column, you go one by one through your list of scores, making a tally mark for each score next to its corresponding value on the list. And then you tally up all those marks to find your frequency for each of those particular values. In column 3, you figure the percentage of scores for each value. So again, you do this by dividing the frequency for each particular value by the total number of scores that you measured. So here's a visual description of how you would do this. Here is your range of possible values on that stress scale. And here are all of the scores you obtained. And you're creating a tally mark next to every score or every value pertaining to recording that score. Now, frequency tables can also be created from nominal variables. So an example is shown here below with a categorical variable. Who is the person who is closest to you in your life? And instead of numerical values, we have categories as our values. So you could feel closest to a family member, a non-romantic friend, a romantic partner, or another entity not listed specifically here. Now, in column 2, this is the frequency of scores pertaining to each of these particular values. 33 people felt closest to a family member, 76 felt closest to a non-romantic friend, whereas 92, the vast majority, felt closest to a romantic partner, and 7 felt closest to another entity that wasn't listed specifically here. Column 3, again, is the percentage of each of scores pertaining to each value out of the total number of scores. Now, frequency tables can also be grouped. So when the variable can take on a very large range of possible values, it might be necessary to lump together intervals of values in the leftmost column instead of displaying every single value. So if your scale has 50 values, you might be best listing the intervals of values rather than every individual one. So I'd like you to pause the video here to take part in an in-class exercise where you will create a frequency table from some data here. So a researcher asks a pair of participants in a study to have a brief introductory conversation and then rate the conversations for awkwardness on a 1 through 9 scale. This researcher thinks perceived awkwardness will be correlated with or related to participants' levels of self-esteem. And here are the first 20 participants' awkwardness ratings. So these are your scores. So I'd like you to draw a frequency table of these data, including the value, its frequency, and percentage. And you can calculate the percentage using a calculator or Microsoft Excel or LibreOffice or Google Sheets. So hopefully that wasn't too bad. And we'll move on now to talk about histograms, which is a faster and possibly better way to visualize a set of scores. Now, a histogram is essentially a bar graph version of a frequency table, with the height of each bar representing the frequency count. So instead of this being in column 1, the possible values on your scale are displayed on the x-axis, and the frequency count is displayed on the y-axis. So if you imagine this being the stress scale from earlier, value 3 is the value with the highest number of scores, or the highest frequency of scores, with 4 participants responding as having a level 3 stress rating. Now, like histograms, or rather like frequency tables, histograms can also be grouped into intervals. These intervals can be called bins at times, where instead of having every individual possible value on the x-axis, you have a range of possible values. And again, on the y-axis, you have the frequency of each value. So the steps for creating a histogram are as follows. Step 1 is to create a frequency table of your data. Step 2 is to put the values or the midpoints of your intervals along the bottom of the page or the x-axis from left to right, from lowest to highest. And 3 is to make a scale of frequencies on the y-axis that goes from 0 to the highest frequency present in your data. Finally, step 4 is to make a bar above each value with a height matching the frequency of that value from your frequency table. So again, I'm going to ask you to pause the video to do an in-class exercise, and I would like you to draw a histogram for the following data. So I asked 10 students the number of times they exercised per week and obtained the following scores. So I'd like you to first create a frequency table and then convert this into a histogram to display these scores graphically. So when creating a histogram, it is important to choose your bins wisely. So I mentioned earlier that a bin is the size of the interval that each bar depicts. And in choosing your bin width, these things need to be considered. 1, if possible, the bins should not touch each other. That means no bins should have 0 frequency for the values in that range. And 2, there should be a good sense of the shape of the distribution. So bins should not be so wide that the general shape is lost. So I'll ask you for a moment, which of these bins seems to best describe the data, conveying the overall sense of the distribution without too much or too little information? So personally, I find the middle display here to be the best presentation of the data out of these three options. Now, the one on the left has way too much information, so much so that because the bins are so small, you have some bins that don't have any frequency. So this is one way to lose the shape of your distribution on account of poor choice of bin width. Now, on the right, you have too little information. You can kind of see from the middle distribution that there are actually two peaks in this distribution, but this information is lost when the bins are so large. So the middle display here is probably the best way to capture the shape of this distribution of scores. Now, a little more on the shape of frequency distributions. What frequency tables and histograms are attempting to convey is indeed the shape of the underlying frequency distribution. In other words, that is how participant scores are distributed across the range of possible values. Now, various facets of the frequency distribution can be described verbally. So let's take a look at a few ways in which that is done. So question one about shape is how many peaks are there? So if you look back at that student exercise earlier where you drew histograms, are the data clustered around one peak or two, or possibly even more than two? So when a distribution is clustered around one central peak, this distribution is described as unimodal. If a distribution has two fairly equal peaks, it is referred to as a bimodal distribution. Now, if there are more than one peak, so that is if the distribution has two or more peaks, it is referred to as a multimodal distribution, which of course includes a bimodal distribution. Now, the fourth type of distribution is a rectangular or uniform distribution, wherein values have roughly the same frequency. I'll show you visually what these would look like in the next slide. Right, so in your unimodal distribution, all of the values are clustered around one central peak right here. And this is when you can draw a cohesive bell curve shape over your distribution. Now, bimodal distributions have values or scores rather that are clustered around two central peaks. Now here's the uniform or rectangular distribution where all values roughly have the same frequency of scores. Now here's a multimodal distribution with three peaks. You could call this a trimodal distribution, if you will. Now, in social science, most of the variables that we wind up measuring tend to be roughly unimodal in their distributions, with the majority of scores clustered around one central peak. Now, another question you might ask about the shape of a distribution is it symmetrical or skewed? Now, if there are roughly equal frequencies of values on both sides of the middle portion of the distribution, this distribution is symmetrical. But asymmetrical distributions can take on different shapes. So a negatively skewed or left skewed distribution is one in which the mass of scores is clustered on the right side of the distribution. So a negatively skewed distribution has a longer tail on the left side. Now, conversely, a positively skewed or right skewed distribution is one in which the mass of scores is clustered on the left side of the distribution, and thus has a longer tail on the right side. So here's what this looks like visually. For a positive skew, most of the scores are clustered on the left side of the distribution. So keep in mind these are scores with lower values, and the higher values wind up in the tail. So there are fewer scores representing higher values in a positively skewed distribution. Now, in your normal curve, or a symmetrical distribution, you have an equal frequency of scores on either side of this midpoint. Now, in a negatively skewed distribution, scores tend to cluster on the right side of the distribution, or along the higher values, with a smaller number of lower values being represented by scores. Now, one thing to keep in mind here is that the side with fewer scores is considered the direction of the skew, counter to the way skew is used informally. So a positive skew means there are fewer positive scores in a distribution, whereas a negative skew means there are fewer negative scores in a distribution. This is somewhat counterintuitive, so keep this in mind. Now, in line with discussion of skew, is the topic of floor and ceiling effects. So when scores are mostly distributed towards the positive end of observed values, this can be called a ceiling effect. So for example, if I were to ask all full-time students, how many classes are you taking this semester? You would see a clustering along the positive side of the distribution. And this would be a ceiling effect. It would also be a negative skew. Now, on the other hand, when scores are mostly distributed towards the negative end of the observed values, this is called a floor effect. So if I were to ask college freshmen, how many children do you have? This group of participants would likely have fewer children than the general population and would likely show clustering of scores towards the lower end of that distribution. And this would represent a positive skew and a floor effect. Now here's visually what that would look like. On the left here, in red, you can see a negatively skewed distribution where a ceiling effect is present. So most scores are clustered along the extreme positive values of the scale. And on the right here, you can see a positively skewed distribution with a floor effect in place. Right, so most scores are centered around these very extreme negative values, or rather lower values, representing a positive skew, right, because you have the tail on the positive side, and a floor effect. Now, the third topic you might question a distribution about in respect to its shape is whether or not there are more scores in the middle of the distribution or the tails. And the standard of comparison here for answering this question is the bell-shaped normal curve depicted below. So some distributions have fewer scores in the center or more scores in the center than the normal distribution. This normal curve here is also referred to as the bell curve or the Gaussian distribution in some contexts. Now, this question of whether or not there are more scores in the center or the tails of distributions pertains to a statistic referred to as kurtosis. Now, distributions with narrower, more extreme peaks than the normal distribution are higher in kurtosis, and that can be seen right here in the center. So this very peaked distribution is high in kurtosis. It has positive kurtosis, and it's also referred to as a leptokurt. Whereas this flatter distribution, flatter than the normal curve, which is overlaid, has a negative kurtosis. So this is lower in kurtosis and is often called a platycurt. Right, so kurtosis is giving you a sense of the extent to which scores are clustered more in the middle or more in the tails. And kurtosis can take on positive and negative values. Now, the final topic I'll talk about for this chapter is graphicacy. Now, graphs, of course, are a great way to quickly visualize data, but they can also be abused with the intention of misleading others. And I'll talk about a few ways in which this can be done. So the first way that graphs can be misused is by not using equal interval sizes. So at a quick glance, if you look at this graph depicting the commissions to travel agents in 1976, 1977, and 1978, it seems that in 1978, this patterned bar, commissions are dropping drastically as compared to the previous 2 years. But if you apply some greater scrutiny, you can see that this pattern bar is only representing the first half of 1978, whereas these solid bars are representing the entire years, 1976 and 1977. Therefore, if the current trends continue, commissions are going to continue to rise in 1978. Since this is only representing commissions for half of the year, this might be doubled, and thus representing higher commissions in 1978 than 1976 and 1977. So it's important to use equal intervals when displaying information graphically to convey accurate interpretations of trends in data. Now, truncated graphs are another way that graphs can be misused to misconstrue distributions of data. So when you look at a graph, you need to ask yourself, what is the scale on the y-axis? Are they showing you the full range of possible values, or is it a zoomed in truncated version, which would exaggerate differences between groups? So at a quick glance, it looks like there are some major differences between groups on this graph. But if you zoom in and consider that this is a 0 to 5 scale, we're only getting a very small snapshot of that scale, which makes these differences look very drastic when in reality they are quite minuscule. So it's really important to show the entire range of possible values on the y-axis of a graph to accurately display differences between different groups of measurement. Now, a third way graphs can be misused is by not displaying axis labels. So this graph shows the average salary for adjunct professors at 4 colleges, and at first glance, they seem quite different. It seems like these different colleges are paying adjunct professors drastically different amounts of money. But if we apply greater scrutiny, we really can't make this judgment because there's no label on the y-axis. So it could be that this is showing $5,000 each individual line here, an additional $5,000. So let's say this is roughly $15,000 salary. This would be a $20,000 salary. That would be a pretty large difference. But maybe it's cents. And in fact, these differences are very small. So without an axis label on the y-axis, we won't really be able to know our scale of measurement, and we won't be able to make comparisons across groups. Now I'm going to finish off this lecture and this chapter with a quote from Tufte from the Principles of Graphical Excellence. Graphical excellence is that which gives to the viewer the greatest number of ideas in the shortest time, with the least ink in the smallest space. So this is to say that you want to show enough information to accurately convey your data, but not too much information that the actual pattern gets obfuscated by superfluous detail. So for next Monday, this should say Monday as opposed to Tuesday, you'll want to have access to my stat lab because the first homework assignment will be coming up soon, not immediately, but soon, and you want to get this in place beforehand. And I will also want you to begin reading textbook chapter 2 according to the class schedule. Well, thank you guys for listening, and I hope you guys have a great weekend, and I will see you next week.